So this is a static equilibrium problem just to show you how they're done, and we'll do one together in class also. But I first want to show you about drawing what's called a free body diagram. So if you've taken physics at any time, you've heard this phrase. And basically you free the body that you're looking at, so this box, from whatever's holding onto it, pushing it, pulling it. So you essentially cut the cables and show the force that's happening because of those cables. So I'm going to call the one that's heading towards the left T1 for the tension in cable 1, and the one that's heading the other direction T2 for the tension in cable 2. And then straight downward, I'll just call it B for the box. We just indicate a downward arrow showing the force of gravity acting on the box. So essentially this dot in the middle is representing the box, and then you show all the forces acting on the box. So there's gravity pulling downward, one cable pulling to the left, and we see that there's an angle of 25 degrees with the horizontal. So we know that this angle will also be 25 degrees. And then the cable on the right has an angle of 40 degrees with the horizontal, so we know this angle will also be 40 degrees. So the idea of static equilibrium is the sum of the forces is 0. So if we write the vector equation, we'd say vector T1 plus vector T2 plus vector B has to equal the 0 vector. It's a lot easier to do if we break it down into two separate problems where we say, well, the only way all the forces will be 0 is if the sum of the forces in the x direction is 0, and the sum of the forces in the y direction is also 0. So we break it down into two separate problems. So we're going to look at vector T1. This is vector T1. Sorry. Get my little eraser. Okay, this is vector T subscript 1 with a vector arrow on it. It can be broken down into two components as we talked about today, where this one would be called T sub 1, we'll call it sub x for the x component of T1. And this vector would be T sub 1y. And so with vector addition, we can say T1x plus T1y has to equal vector T1. So we also talked today about, well, how do I find vector T1x? And we said, well, that's going to be the magnitude of vector T1x times the cosine of the 25-degree angle here to get the x component. So 25 degrees. And it's going to be in the negative I hat direction. So we're writing it as a vector now. And we're going to say whatever the magnitude of T1 is, sorry, this is just T1, not T1x. Okay, so what T1x vector is the magnitude of T1 times the cosine of 25, because this is the magnitude of T1x, times the direction vector, which is negative I hat. So we're going to say that to the right is positive and up is positive. Okay, so then we also can see that T1y is then going to be the magnitude of T1 sine of 25 degrees. So this is the magnitude of T1y. And this is going to be times j hat, positive, because it's pointing upward. Okay, so in a similar way, we can break vector T2 into its components, T2x and T2y. So vector addition tells us T2x plus T2y will equal vector T2. We can see that from the picture. So this is the 40-degree angle. So vector T2x is going to be magnitude of T2 cosine of 40 degrees I hat, because it's going in the positive x direction. Then T2y is going to be magnitude of T2 sine of 40 degrees j hat, because it's going upward. Okay, so now let's make a little simplification, and let's let A be the magnitude of T1. So that's going to be how much force is in cable 1. Then we'll let B equal how much force is in cable 2, the magnitude of T2. That's just going to be easier to write our equations this way. So the sum of the forces in the x direction is going to be negative A cosine of 25 degrees I hat plus B cosine 40 degrees I hat, and that has to equal the 0 vector. The only way that's going to be the 0 vector is if negative A cosine 25 degrees plus B cosine 40 degrees equals the scalar number 0. So now we have an algebraic equation. Okay, then we're going to do the sum of the forces in the y direction. And so we have, for T1y, we have A sine 25 degrees plus B sine 40 degrees. Now we have minus 1,000 for the weight of the box, which is pointing downward. So if we go back up here and write vector B as a vector, we'd say it's negative 1,000 j hat, because it's pointing downward. So I went right to components this time and didn't put all the j hats and then remove them, because that's just going to simplify things. So now basically what I have is something like 2x plus 3y equals 0 and 3x minus 5y equals 10. And that's a system of equations. So here's one equation. Here's the other equation, two unknowns, two equations and two unknowns. So remember, to solve this one, you would have multiplied by, say, negative 3 on both sides of the top equation, and then by 2 on the second equation, so that you would get a negative 6x and a 6x, and the x's would cancel. What's the same idea here? So the first equation, I'm going to multiply on both sides by sine of 25 degrees. So I have negative A cosine 25 degrees plus B cosine 40 degrees in parentheses, so I distribute. And then at 0 times, oh, nothing's going to happen there, is it? So I'll still have 0 on the right. So then to get a matching coefficient, I need to multiply the second equation by cosine 25 degrees on both sides. So let's do that. And when I multiply by the cosine of 25 degrees on the right, I'm still going to get 0. So we have negative A sine 25 degrees cosine 25 degrees plus B sine 25 degrees cosine 40 degrees equals 0. And then we have A sine 25 degrees cosine 25 degrees plus B times cosine 25 degrees sine 40 degrees minus 1,000 cosine of 25 degrees equals 0. So now when we add these two equations together, this first term in each equation is going to cancel because they're exactly opposite. So that's going to leave us with B sine of 25 degrees cosine of 40 degrees plus B cosine of 25 degrees sine of 40 degrees. And then I'm going to put the 1,000 cosine 25 degrees on the other side by adding it to both sides. So now I have two copies of B, but that's what I want to solve for. So I'm going to factor out the B. And then I want to solve for B, so I'm going to divide both sides by this long quantity. Sine 25 cosine 40 plus cosine 25 sine 40. Divide both sides. sorry about the detour, plus, okay, sine 25 cosine 40 plus cosine 25 sine 40. So now make sure your calculator is in degree mode and compute this. And I'm getting that B equals 1,000, and it's approximate because it's lots of nines, 999.9999. So it's about 1,000 pounds. So don't forget the units of pounds. So that's the amount of tension in the second cable. So that's one part of the answer. And then you can use either of the two equations you started with up here to solve for A. So let's use negative A cosine of 45 degrees, cosine of 25 degrees, negative A cosine 25 degrees, plus, and B, we'll use the B we got in our calculator, but we'll write 1,000 for approximately, cosine 40 degrees equals 0, and then let's solve for A. So 1,000 cosine 40 degrees equals A times the cosine of 25 degrees. Solve for A, divide both sides by cosine 25. And we're going to get that A is approximately 845.24 pounds. And that's the magnitude of the tension in cable T1. So those are the two parts of the answer that you need.